Quantum mechanics alters the laws of physics on microscopic scales, but what do we mean when we say microscopic scales? Today, we're going to investigate that by interrogating the parameters of quantum mechanics, that is to say, Planck's constant. Let's get started. Physical models depend on parameters. This we've known for a long time. Typically, models come from a lot of experimental observations, and then we deduce the laws of physics from there. A famous example of this is Newton's law of universal gravitation, which is a central force law, which basically tells us that the force of any two masses upon each other is an attractive force, and that force has a magnitude that varies linearly with both masses and inversely with the radial distance between those masses squared. Finally, that force is proportional to a constant that sets the scale for how strong gravity is. And we have come to call that constant G. Now, the force of gravity is really, really weak, as evidenced by the fact that it takes the entire planet Earth to keep us seated on the floor. But if you'd like a more quantitative approach to the weakness of gravity, we can just simply look at that constant of proportionality. We can look at that constant G. G is something like 6.67 blah, 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 times 10 to the minus 11 joule meters per kilogram squared. There are, of course, other forces, and other forces have very similar laws, like the force of electromagnetism. Electromagnetism similarly has a 1 by r squared form. That is to say, given two particles, each with its own electric charge, the force due to the electric field between them is linear in both charges. Again, inversely proportional to the square of the radial distance between the two particles, and is also proportional to a constant that for historical reasons has come to be called 1 over 4 pi epsilon naught, the vacuum permittivity of free space or whatever. Regardless, it has a very similar structure to that of gravitation. To get a sense for the strength of the electric force for Coulomb's law, we can look at its constant of proportionality, that 1 over 4 pi epsilon naught, evaluated numerically, which is something like 8.99 times 10 to the 9 joule meters per coulomb squared, which appears anyway to be much bigger than gravity's proportionality constant G. But it's a little difficult to really compare them because kilograms and coulombs are just not the same thing. So in order to really compare the forces of gravity with the forces of electricity, we need to find something that has both an electric charge and a mass. So for us, for today, we'll be considering subatomic particles, that is to say, protons and electrons. So the total force between the proton and the electron is the sum of the electric force and the gravitational force between the two. To compare both forces, we can simply evaluate using the known masses and the known charges and the known constants of proportionality for each force. And we can ask, okay, so what's the relative strength of the electric force to the gravitational force? And for this case anyway, we see that the electric force, Coulomb's law, completely dominates the interactions between the proton and the electron. The gravitational force is just incredibly, incredibly weak. It's negligible for all intents and purposes. And this makes a lot of sense, right? Because if we look at the physical scales involved in the different forces, gravitation is the thing that binds planets and stars together, right? And so a typical planet in our solar system orbits the sun at a distance of something like, a few hundreds of thousands of miles, or a few like hundreds of millions of miles in the case of like Jupiter and Saturn and so on. Whereas for the case of the atom, the electron tends to orbit the proton at distances that are more akin to like the sub-nanometer scale. So we talk about different kinds of physics operating at different kinds of scales. That's what we're talking about. Gravitation operates at the hundreds of thousands of mile scale, and electromagnetic interactions operate, on the atomic scale. And fortunately for us, for the study of quantum mechanics, almost everything that we're going to have to deal with happens at the atomic scale. Different kinds of physical phenomena, like the force of gravity and the electromagnetic force, all have their own characteristic scales associated to their own characteristic parameters, like g and epsilon naught. What's somewhat unique about quantum mechanics is it applies across the board to all physical phenomena, as we will eventually learn. Quantum mechanics, too, has its own characteristic scale and its own parameter. Planck's constant, h, sets a fundamental resolution to information density in space and time. The precise value of h isn't particularly illuminating. It's something like 6.63 times 10 to the minus 34 joules seconds. To get a better intuition for how h applies, particularly in scales relevant to atoms or chemistry, it's helpful to introduce another physical parameter, another constant of nature, the speed of light, c. The speed of light represents not just the velocity of particles of light, but also it puts a fundamental speed limit on how fast information can travel through space and time. C is just shy of 300 million meters per second. The precise value isn't terribly important or intuitive or useful a priori, but what is useful is the product, h times c. H times c by itself looks something like 1240 electron volt nanometers. An electron volt, remember, is just a unit of energy and can be represented in the more human-friendly joules, but it's basically the amount of energy that you have with one electron held at 1 volt. So if you have a 9-volt battery plugged into something heuristically, you can think of that as all of the electrons coming out of that 9-volt battery being spit out at 9 electron volts worth of energy each. We'll revisit this idea of comparing things to h and hc a little bit later in the course, but for now, it's for all practical purposes. Let's just say when we have something that looks like a length times an energy, we begin to worry about quantum mechanics when that quantity, that product, starts to approach the smallest kind of possible size that we need to concern ourselves with, right? That 1240 electron volt nanometers. To test out this relationship, this scale of quantum mechanics, we can take a hard look at 1240 electron volt nanometers and say, okay, well, what do we know? What physical item is on the scale of a nanometer or so? And the first kind of most obvious thing that occurs to me anyway is the wavelengths of visible light. The wavelengths of light, fall on a spectrum from red to violet, at least the visible spectrum, and those wavelengths are about 400 nanometers for the case of violet light to about 700 nanometers for the case of red light. So you might immediately ask, okay, what energy scales associated to these length scales, to these wavelengths of light, are important for quantum mechanics? So what we can do there is simply say, okay, 1240 electron volt nanometers divided by 400 to 700 nanometers gives us an energy scale that's somewhere between 2 or 3 electron volts. In other words, quantum mechanics becomes important for length scales on the order of the wavelength of visible light when we consider energies that are below, about 5 electron volts. And that's a really interesting number because that's not enough energy to rip an electron from an atom. The binding energy of an electron from an atom is about like 13 to 10 or more electron volts. Molecules are bound together with energies of about 10 electron volts. So 2 to 3 electron volts is really important for the dynamics of the electron inside the atom or inside the molecule. In other words, if we want to study the relationships between visible light and the electron, we are obliged to consider quantum effects. Nuclear physics provides us with another really great example. So inside the atom, we have the electrons, of course, but also the nucleus. So for the hydrogen atom, it's just 1 proton, but for other atoms, we have more protons and more neutrons. And again, you can check out the field guide to particle physics to learn all about them from a qualitative perspective. But as it turns out, we can rewrite HC. Instead of 1240 electron volt nanometers, we can write it as 1240 million electron volt nanometers divided by 1 million. a Fermi or a femtometer. The binding energy of all those little particles, those protons and neutrons inside the nucleus, is on the order of 1 to 10 million electron volts, about 1,000,000 times stronger than the bonds between atoms in a molecule. And when you know it, experiments have shown that the typical length scale associated with the nucleus in quantum mechanics is on the order of 1 femtometer, 1 Fermi, 10 to the minus 15 meters. Crazy, right? We've been talking about the atom, the bound states of protons and electrons, from the perspective of Coulomb's law, in terms of forces, in other words. But let's do the standard trick in classical mechanics and consider potential energy. That is to say, we'll consider, because F is a conservative force, we can integrate it to find the associated potential energy. Since the proton is really heavy with respect to the electron, we can consider the proton as the bottom of a potential energy well sourced by the electric field of that proton. And the electron is somehow being attracted towards the proton by falling down this potential energy well. So this is a basic exercise in calculus to simply perform a very standard integral. And we find that the potential energy, if you like, is essentially 1 over 4 pi epsilon naught E squared over R. Or we've assumed for this case that the potential energy of the electron at infinity with respect to the proton is 0. So we can really think of this as a well. And that's what gives us actually this minus sign out in front. Now, just from the simple perspective of this model, we see that if everything were to remain classical, the electron would fall all the way down to R equals 0. That is to say, it would fall way down and slam into the proton. The atom, in other words, would not be stable if not for quantum effects, because we know that the atoms are in fact stable. We know that the electron stays at a specific distance from the proton. That specific distance is observationally to be about an angstrom, 10 to the minus 10 meters. So clearly at some point our classical intuition breaks down. This 1 by R potential breaks down. How this potential breaks down is a question for quantum mechanics, and it's a question that we'll get to in this course. But for today anyway, a better question to ask is, where does it break down? At what value of R? To see that, let's appeal to the scale of quantum mechanics that we reviewed earlier. That is to say, let's appeal to the product HC. So heuristically anyway, the orbit of the electron around the proton is about an angstrom, 10 to the minus 10 meters. So let's just plug that number in to this potential energy and see what we get. So we already know what 1 over 4 pi epsilon naught is. We already know what the value of the electric charges are. So divide all that by 1 times 10 to the minus 10 meters, and we find an energy that's about 14 electron volts. That's pretty remarkable, because the actual answer given to us from quantum mechanics, it turns out to be 13.6 electron volts. So it's really close, but this is more of an accident, really, than anything else. Right, so let's not get ahead of ourselves. Let's now appeal to our scale of quantum mechanics, this HC, 1240 electron volt nanometers, and ask, okay, so how does 14 electron volts compare to this scale? And what lengths, in other words, make us have to concern ourselves with quantum mechanics? So dividing 1240 electron volt nanometers by 14 nanometers, we find a length scale that's on the order of about 88.5 nanometers, which is much larger than the angstrom, which is much further apart than the proton and the electron typically are in an atom. In other words, to consider the physical problem of the hydrogen atom, of an electron orbiting around a proton, we have to start worrying about quantum mechanics almost immediately, as soon as the two approach each other. Atoms, in short, are definitely something that we need quantum mechanics to describe. And describe these ideas in quantum mechanics we will. That is the primary goal of this course. But for today, we have now started to gain familiarity with some of the scales involved, some of the constants involved, some of the ideas involved. We'll be playing around a lot with Planck's constant H and HC, the combination, in the days to come. So stay tuned for more.